Excellent. Hello, everyone. You're a new face. I haven't seen you here yet. What do you do research on?
I'm in IFA.
Okay. Cool. Exciting. Okay, for the computational imaging folks, today's lecture will probably not be very interesting. I apologize in advance. I was just asking around, actually, like, is anyone here doing computer vision research? Who is doing computer vision? Or you do computer vision? What do you do research on?
Also, like 3D reconstruction, nerd stuff.
Cool. With whom?
So currently I'm working with Professor Esper Pfister at Harvard.
Oh, of course, yes.
I'm also like working with Joseph Gonzalez at Berkeley with the undergrad advisors.
Very cool. And you're also in Hans-Peter Pfister's lab. Okay, very cool. Who's from Harvard? Okay, 3 people from Harvard. Cool. Anyways, enough Q&A, I guess. Thanks, everyone, for coming again. It's always cool to see people showing up for the lecture. Today will be the last lecture without a pure, basically, differentiable programming and deep learning focus. So we had a few of these lectures now, which were basically just concerned with basics in geometry, basics in like 3D representation, and like we were slowly building up. It's like a little bit of a drag. I hope you, I mixed it up a little bit with having this depth prediction lecture in there. Going forward, we'll have lots of deep learning and lots of cool machine learning models. We're just like catching up on like some basics still. So today was going to be the last lecture on like catching up with basics, which is going to be on rendering and like a super rough overview of rendering in like computer graphics. And like I called the lecture, like usually in the notes in the syllabus, it's called light transport because as we had discussed before, what is graphics? Graphics is concerned with the math and the modeling that is required for having given like some kind of representation of a 3D scene. We already discussed some of these, right? Like meshes, for instance. How can we model how light bounces around in the scene to then form images on the sensor? That's what computer graphics is concerned with, right? And then lots of other cool stuff like animation and whatnot, which we're not talking about at all, basically. So today we'll talk more about that stuff. So all of the stuff we're talking about today is really concerned with the forward model. So it's concerned with the model that goes from 3D scenes to images, where this lecture is called inverse graphics, because the thing that we are building up towards is inverting the forward model. So how can we build models that take images as input and then they reconstruct 3D scenes? And that's what the whole rest of the whole course is going to be about. But today's the last lecture that is going to talk about the forward model. Cool. And why is this interesting? Well, it turns out that in order to build good inverse models, it's oftentimes very useful to understand the forward model in a painstaking level of detail. And so that's what we're doing today. Okay, so first, we already discussed this, but just as a brief review, what is rendering even? So like, let's say we have like some 3D scene like this one. It's, I don't know, it's a bunch of objects, and then there's a light source. The rendering is answering the question, if I place a camera in this 3D scene and the camera has an image sensor, let's say there's a pixel on the image sensor, rendering is answering the question, given the representation of the 3D scene, what is the color of this pixel? What is the color of the pixel that the camera is going to record when I take a picture with my iPhone right now? So rendering can be defined as a function. It's a function that takes as input a representation of the scene, a 3D scene representation, and then it takes as input a parameterization of a camera ray. And then it gives you basically the radiance of the ray, or it gives you, and we're going to talk about what radiance means. And it's actually quite useful to think about it like that because you can basically think about many different levels of sophistication to implement that function, right? We actually already talked about one of them, which was this depth warping thing. Depth warping that we discussed is also a form of rendering, right? For depth warping, we were concerned with, okay, we have an image of a scene and we have the depth for that image, and now you can answer the question, what does this scene look like when I view it from a different angle? And like depth warping gave you like basically the most basic way of doing rendering, right? And today we'll see in which ways it falls short, or like many ways in which it falls short. Okay, so many of these slides are taken from Professor Karen Liu and Jiajun at Stanford. Jiajun actually used to be here at MIT. Cool, so the high-level thing that I want you to remember from today's lecture is the rendering equation. Who has heard about the rendering equation before? Okay, great, not so many people. So what is, okay, we'll basically look at the rendering equation today, and the rendering equation is basically the thing that tells you how light bounces around in a scene. That's what the rendering equation does here. Okay, so first we're going to talk about radiance. Radiance is basically the fundamental quantity of light that we deal with in rendering. And some of you might know neural radiance fields, so-called because they are a field, which we already discussed, that parameterizes the radiance of every point. So radiance is really like a very fundamental quantity of light. And what is radiance? In terms of physics, radiance is actually a physical quantity, so it's a well-defined physical quantity. It's the density of photons at a point, so like you pick a 3D point, it's the density of photons that flow through that point that travel in the same direction, basically along a line, at a given wavelength. So you pick a wavelength, so actually technically this is called spectral radiance because it's for a given wavelength, but you pick a wavelength and then the radiance basically tells you for a given 3D point in space and for a given direction how many photons pass through there, more or less. So it's energy per time per unit area per unit solid angle per wavelength. Interestingly, like some of you, I think we might have even mentioned this in the lecture already. Some of you might have heard about the light field. You know, there's like we discussed the radiance field, which is the field that maps if I tell you radiance field, now you know what the coordinates are over which the radiance field is defined. The radiance field is defined given a point and a direction. It tells you how much radiance passes in that point in that direction. The light field is a thing that we also always often deal with. It's basically the field that gives you for a given ray. You just pick a ray and you basically just ask, forget about the point, just along that ray, what color would you observe along that ray? So if I built a sphere around my head and I like pick a ray that exits the sphere, like what color is this ray going to see in the scene? And like if I move my head around here, this is basically like sampling different rays from the light field. Okay, so it's basically so this is actually the radiance field. So you have a position, you have a direction omega, and you have a wavelength, and this is radiance vector plus 1. Okay, radiance intuition. So basically, this is basically just trying to make one point, which the radiance along a ray in free space is constant. So the radiance is a physical quantity. If you pick a ray, the radiance along that ray is constant. That's kind of almost how the radiance is defined. So if you take a point light source, and here we have a 2D radiance meter, which is basically, you can see it's a point, right? And it's a circle. The circle tells you the direction, and the point tells you you sample the position, and you sample the direction. Then the 2D radiance meter will basically tell you that at that point, in that direction, you can measure a given radiance. And along that point, in that direction, you could measure a different radiance. So the radiance is different, is a function of the direction, right? And the other thing is that the radiance along a ray always stays constant. So the radiance along this ray would stay constant, right? So this is okay. And then a few things happen. So just to give you some intuition, if you take a picture of the sun, or like if you take a picture of a light source, if you're closer to the light source, then the light source will appear brighter on the pixels, right? And if you go further away from the light source will be dimmer. So how does that fit together with the fact that the radiance along a ray stays constant? Yes? Exactly, right. It's basically the area that you're integrating over. So like imagine the light source, imagine there's like a sphere that is expanding around the light source, and as you get further away, basically you're integrating over a smaller area at the original light source. Does that make sense? So in other words, like imagine that, this is actually not very visualized very well here, but basically you'd be integrating over a smaller area. The light rays that imagine you have a pixel in your camera, and that pixel is integrating over all the light rays that are coming from the light source and that are intersecting with that pixel. And those light rays will basically be fewer the further you go away, and that's why the radiance that you'll measure is smaller. Okay, radiance along an unblocked ray is constant. Response of sensor is proportional to the radiance of the visible surface, right? So this is exactly the point. If you like basically imagine that there was a light sphere that is emitting light in every direction, then it's very intuitive as you go. Forget that, whatever. Okay, good. And then this is something that we'll talk about in a moment. This is something that is going to be important for understanding how the radiance bounces, or like how light bounces around in a scene. The radiance of the light that is reflected at any 3D point in space has a relationship to the amount of light that is incoming at that 3D point in space. So like in the real world, right, like some surfaces or like some points in 3D emit light, and some points in 3D space do not emit light. So like all the light sources in here, or like the sun, they emit light. This table here is not in itself emitting light. But of course, my eye is still receiving light from this table because light is like coming into this table at every point, and then the table is reflecting some of the light back towards me. Okay, and how is that? How is of course, computer graphics folks have come up with a way of describing how a given material reflects light in that way. And this is actually the thing that makes different surfaces look different in terms of like shininess and things like that. And this function is called the bidirectional reflectance distribution function, which is a mouthful, the BRDF. Who's heard about the BRDF before? Okay, a few people. Good. So the BRDF. What is the BRDF? The BRDF is exactly the function that tells you the ratio of the outgoing radiance with respect to the incoming radiance as a function of the two angles. So you pick a 3D point in space, and then for that 3D point in space, you have the angle of the incoming light, or the omega of the incoming light. You have the omega of the outgoing light. And now the BRDF is basically the ratio of these two, is the degree to which the surface is reflecting light in that direction. So now, one thing, what is the upper limit for the BRDF? Like, what's the 1? Exactly, it can be maximum 1, right? Like, it can only give you like all of the light, right? It can't. The surface shouldn't be, unless it's emitting light, of course. But then that doesn't make sense. So the BRDF describes how a material is reflecting light, and the Helmholtz reciprocity is also an interesting and important property, which tells you that light paths are, and this is actually exploited in rendering, as we will see later. Helmholtz reciprocity is the concept that tells you that light paths are invertible. So if you pick a light path, like if I place my camera here, and like imagine this was like a perfect mirror, and there would be like a point light source somewhere over there, then the light would be reflected like that. And if I swapped the place of the light source and the camera, I would put them in the opposite order. The BRDF is symmetric, so the surface will this ratio is not dependent on the order of the light source and the sensor. Does that make sense? Good. Okay, so some intuition. So the BRDF. Let's look at the BRDF for a set of 2D surfaces. So like these are 2D surfaces, and in these cases, I should say 1D surfaces actually. And in these cases, the BRDF is going to be a function with degree 2, right? So we have one scalar, which is the angle of the incoming light. There's one scalar, which is the angle of the outcoming light. And the BRDF is going to tell you the ratio between, is basically going to tell you how much light is reflected. So for a perfect mirror, what should this function look like? Like a mirror that reflects light perfectly. It doesn't lose any light, like light is incoming. Yeah. Right, it is a, right, I think yes, exactly. It's a delta function, just except for the case that it's kind of a line, right? Because as you vary the angle, there's always, given an incoming angle, there's always going to be exactly one outgoing angle at which you get the reflection. So if you look at exactly right, if you only look at a given incoming, if I fix the incoming direction, the light of the incoming ray here, the angle of the incoming ray here, which is the theta I. If I fix the theta I, then exactly as you say, the BRDF conditioned only on the theta 0 is going to be exactly a point. It's going to be exactly a Dirac pulse, because only in that one direction is the surface emitting light back. Makes sense, right? It's like pretty clear. Okay, so now you imagine you have a slightly rough mirror. Like you have a mirror that is not perfectly refractive, but it's slightly rough. Like what would you expect the BRDF would look like? I mean, it's not like slightly rough is not a very good question, because what does slightly rough mean? But you would imagine that basically, given a certain incoming direction, maybe there's some variance in the directions where there's outgoing light. So maybe it's going to look something like this. So it's going to be basically noisy along the main diagonal. A retroreflector. Does everyone know what a retroreflector is? It's like it's a surface where when you shoot light into it, it'll reflect light exactly back into the same direction. So like you all know this from like the stuff that you're wearing when you're biking outside, like these warning vests, these are retroreflectors. So like they're basically trying to reflect the light in exactly the same direction where it came from. And shouldn't be too surprising, the BRDF in this case will basically look like a diagonal still, but it's going to be a diagonal in the other direction. Okay, slightly more interesting. What does the BRDF of a so-called diffuse material look like? So of a material that isn't, so all of these materials that we discussed so far are like in some way shiny. So this is what you would call like metallic or shiny. So polished materials. What does the BRDF look like for material that's not shiny at all? Yeah.
For any incoming angle, it evenly distributes the light across all outlets.
Exactly. So, actually, yeah. So, sorry, I jumped ahead. That's exactly right. For a material that isn't shiny at all or diffuse, it's exactly what you just described. So the BRDF would basically is like a perfectly scattering function. So like for any incoming angle, it's perfectly random. And I should say the BRDF is like a model. Like where does this model come from? It comes from a model of having, it's kind of modeling a surface as microscopic little mirrors. As like for every square millimeter, you have like millions of microscopic tiny mirrors. And you can imagine in a mirror, in like an actual mirror, in a macroscopic mirror, all of these tiny mirrors are like aligned perfectly. And that's why statistically, if you shoot a ray in, it'll only be reflected in one out. But in paper, you can imagine they're like perfectly random. They're like completely random. And that's why when a ray hits there, like it's just distributed in all directions, right? Okay, so paper actually, any surface that is a mix of like diffuse and, like actually, for instance, these armrests are something where the BRDF would look like that as well, where maybe they have like some specular components, so they have some shininess to them, but also they have a component where it's basically like has an aspect of this diffuse nature to it. Any questions? Yes?
So how we define the BRDF, it's not going to be able to handle like anisotropic like reflection of lights, right?
Anisotropic reflection of light. Can you say what you mean with anisotropic reflection of light?
Yeah, so like basically like light is just not reflected like across like the same distribution, but rather it's gonna like point to a particular direction, like depending on the angle of like incidence.
Can you give me like a lens, you mean, for instance? Like if you have a lens and like it converges the light, or what?
Some kind of like metallic texture that has like vertical like bars on them, or like
Like brushed metal, where if you look at it from one.
So I think this is a good question. So I think in principle, like the thing that you just described is still modeled by a BRDF just fine, right? Because there's just going to like be one chunk of like the incoming outgoing light thing where it's going to be looking one way and one chunk in which it's going to look a different way. So, but I'm not quite sure. You mean like a spatially varying BRDF basically? Is that what you mean? Yeah, like you mean a BRDF that is different at different points of the material. Like you have like a surface and then you mean it seems like the BRDF is different at different points in the material. Yeah, I think that is just modeled as a spatially varying BRDF. Yeah. Yes?
So if it was perfectly diffused, it would be like completely black. You're saying there's some specularity.
Yes, exactly, yeah. Yeah, if it was perfectly diffuse, it would basically be like, okay, the outgoing, exactly. Cool, and then, yeah, there's like a few more things. If like there's, okay, good, makes sense. I think this is about as much intuition as we need. So, and now for all of these materials, basically, the BRDF is telling you what the material looks like. So the BRDF, I should also say, you can have different BRDFs for different wavelengths, right? So maybe some wavelengths of light are absorbed. So yeah, what would something look like? What would like a perfectly black surface look like, right? Perfectly black surface would just be empty. Like there's basically, the BRDF is zero in every direction. Like it doesn't matter whether there's incoming light or not. Nothing is reflected and everything is converted into heat. If you have, so the BRDF can also be wavelength dependent. So maybe some wavelengths are absorbed and some wavelengths are reflected. And then that's how you can express color. And then shininess versus diffuse basically tells you what's the what's the direction, like if the BRDF is has a preference for the incoming versus outgoing direction. So all of these different materials can be parameterized by some BRDF. And in fact, oftentimes this is if you like open Blender or some 3D editing tool and you load up a material, you'll basically load up a BRDF that parameterizes this material. Okay. Then this is another thing to be aware of, like the incoming light. So like if you we already discussed that if you have a pixel is basically integrating the radiance over a surface. So it's basically saying for every point, like you're basically integrating over the surface of the pixel and along the directions of the wavelength. So now imagine you had like your pixel, but your pixel might be actually, yeah, this is good. So imagine both of these would be the same pixel. Actually, it doesn't make sense. Okay, the purpose of the slide is just to say if you have a surface that is perfectly orthogonal to the light source, then what is the density of photons on the surface? Versus if the surface is slightly slanted, then what's the density of photons on the surface? And of course, the density will be lower in one case than in the other, right? Like you have the same amount of photons incoming, but it's distributed across a larger surface area. Yeah, and the density of photons is therefore like proportional to this angle. So like as you're varying the angle, the density of the photons is changing. And this is now something we're going to exploit actually in a moment for rendering. So because let's think about this. So like the cosine theta of I can be parameterized as a function of the dot product. So if you have the dot product, like if you have the surface normal of the surface normal is pointing in this direction. And now we know that the cosine of this angle here can be parameterized as the dot product of this surface normal, if it's normalized, together with the direction of this light. That's exactly the surface normal. And so this ratio of the this ratio of the areas can be parameterized as the dot product of the surface normal together with the direction of the light source, with the direction of the light. Cool. And now we are ready to talk about the rendering equation. So what is the rendering equation telling you? The rendering equation is telling you for a given, actually it's annotated in the slide. This is great. So let's talk about this. We're going to go through the rendering equation step by step, and then you know what it talks about. So we have the outgoing radiance in the direction at the point x, so at a coordinate in 3D space. There's an outgoing direction omega 0. So at coordinate x, at a 3D coordinate x, there's an outgoing direction omega 0. And for a given wavelength lambda, so that's what the rendering equation tells you. The rendering equation tells you for every 3D point in space, for a particular ray direction, what is the radiance that is going out in that direction at a particular wavelength. So the rendering equation basically gives you the full picture of the light that is bouncing around in the scene. Like if you had this function for every possible 3D point in the scene, it would tell you everything about the scene you would have to know in terms of the light transport through the scene. And the idea of the rendering equation is to say that using the fact that light comes from light sources and then bounces around in the scene, we can formulate the rendering equation as a function of incoming and outgoing light at every surface. So let's go through that. So let's say we had a point x, and so this is just this quantity. So L is the rendering equation will just tell you for this point how much light goes in this direction. And what is that? So for a certain 3D coordinate and for a certain direction, what are the parameters of the radiance that you will observe along that ray, right? So one certainly is if you're looking at a light source, the light source is just emitting an amount of photons. And if you're looking at a light source, then the radiance will certainly have the component of how much light is emitted by the surface. So if this table here was glowing by itself and you turn off the light and I look at the table, then even right now, one part of the photons that I would receive would just come from the fact that the table is glowing in the dark, which it's not, but imagine it was. Okay, so that's one part. So the emitted radiance is one part. But then, as this table isn't actually glowing in the dark, all of the light that I'm receiving from this table must be light that is coming from light sources that are not this table. So it's all the light that is bouncing around in the scene. And that turns out is kind of hard to compute. But if you for a moment imagine how you would compute it, we already learned about the BRDF. It's basically an integral, right? So like the amount of light that is emitted at the surface into this direction is going to be the BRDF at this point, like, okay, you have a light source Li, so this is the incoming radiance. So imagine there's light source over there. Light is coming in here, so we already know that the BRDF tells you what fraction of that incoming light will be reflected in this direction. So that's the point of the BRDF. This is this function f here. So at this 3D coordinate, what is the BRDF of these two angles? And then you have the amount of light that is coming in at that location. And then you have this dot product, which is basically what's the angle of the light source relative to the ray direction, relative to the surface normal, which basically tells you what's the density of, what's the photon density at this location. So these are these different terms. So the F is the BRDF. The L is, there's a recursive component to it. The L is the incoming radiance at that point for a certain thing, and then you're integrating for all incoming light directions. So you take this point and you integrate over all possible incoming ray directions, and you ask for this ray direction, how much of that incoming light is going to be reflected in the direction that I'm currently looking at this 3D point. Does this make sense? You look like you have a question. No? Good. Yes?
Can you explain again why we use the dot product?
Yes. Good question. Yes. So the BRDF, the rendering equation gives you the thing for an infinitesimal point in space, right? So it's like it's at an infinitesimal point. So this like dot product of the surface normal and the incoming ray direction is basically expressing the fact that since you're looking at a single point, but the thing that you're really interested in is in order to reason about how many photons are reflected at this point, you first have to reason about what's the density of incoming photons at that point. And the yeah, no, I'm actually thinking about that right now as well. I think it's because you're I forgot. Good thing. I have to go back and check myself. Talk to me later. Yeah. Okay, and like this fact here is pretty straightforward. Like of course like the part other than the light that is being emitted from the surface, you have a conservation of energy. So like other than the amount of photons that are emitted from that surface at that 3D coordinate, like the surface can't reflect more light than is incoming. So like the total norm of the integral of the BRDF at that coordinate can't exceed 1. Okay, so now there's the color component to this. So I mean, this is actually pretty straightforward. So like in practice, you have a continuous spectrum of wavelengths, right? So the colors of light are a continuous spectrum. But in practice, of course, like for a different sensor, you all know this. If you have an image of an image, you really only keep track of RGB. You basically say, okay, we have like 3 discrete wavelengths, which isn't in fact true. Like a camera actually has even though it's called the red, green, blue channel, it's not like each of these channels are like a Dirac in the wavelength. They're actually little distributions around like the red or the green or the blue channels. But in practice, like oftentimes you could just kind of say, okay, like we have like one, you could do this for red, we could do this for green, we could do this for blue. So you just have one BRDF for each of the colors, you have one for RGB. If you wanted to like code this up, otherwise you would have to like consider all of the continuous spectrum of wavelengths. Okay, so this is basically the describing how the light bounces around in the scene. But now the question is computationally, how do you actually, if I give you a 3D scene, I give you a parameterization of the light that is emitted across different light sources, how do you actually now computationally approximate this rendering equation? And the key insight here, and this is actually something that's really important to deal with as we move on to differentiable rendering, it turns out that this is a spectrum of photorealism. So like at one end of the spectrum, you're basically simulating all the physical effects that take place in the real world. And there's many physical effects that are extremely complicated. So there's like things that, for instance, light might actually penetrate a surface and then scatter around under within the surface and then only be reflected out again. This is called subsurface scattering, for instance, and this is kind of the thing that makes your skin look slightly translucent. So there's like lots of very complicated effects that happen in lighting. But it turns out in reality we don't have to maybe model all of them because we might not be interested in the level of realism of capturing all of these effects. And it turns out in differential rendering, so when we do inverse graphics, when we do 3D reconstruction, oftentimes the forward models that we invert or like the renderers that we're going to use are like throwing half of these out of the window. In fact, even the reflection that we just talked about, like just the basic idea of reflections, like we have a mirror in the scene and the mirror reflects part of the scene, is something that almost no like inverse graphics method deals with. So you're kind of, there's like 99% of imaging modalities are not considered. So there's a spectrum of photorealism in the kind of renderers that you, in how closely you approximate the rendering equation, basically. And so the simplest thing that people came up with, or like the simplest thing we're going to discuss, is like Phong shading. So, and this is usually what people code up. I think I coded this up before in a graphics lecture. Has anyone coded up Phong shading themselves? What lecture did you code it up in? Yeah, undergraduate graphics class. So Phong shading is like the simplest thing that people code up. And interestingly, Phong shading has absolutely no physical basis. It's actually not a physical, it's not actually a physical forward model of how light transport works. But it turns out that it kind of looks close enough. So it like for making things that look approximately shiny and diffuse, it works well enough. So Phong shading is basically, what we're going to do is we're going to look at different rendering algorithms and how they basically simplify the rendering equation and what version of the rendering equation they actually model. So what is Phong shading doing? We already discussed these things. So we have the reflectance, which is the BRDF, the light source. The light source is in the scene. Then we have the angle weight, which I forgot about. By the way, does anyone remember this? David, do you remember? Yes. Yeah. Yeah. Yeah, that makes perfect sense. But I was also, yeah, that makes perfect sense. But I was also confused about like why doesn't this? I forgot why the light source doesn't already account for that, because the light source is already infinitesimal, right, for like a given unit. So yeah, anyways, sorry that I forgot. Last year I remembered, but this year I forgot. Tells you that I haven't actually had to work with this in a while. But okay, so what does the BRDF look like for Liberian surfaces? We already discussed this. If you have a surface that is perfectly diffuse, so like it doesn't have any preference or like any shininess to it, then the BRDF is just like a flat thing. So it means that the BRDF is actually constant. So if you look at, usually the BRDF is a function of the incoming and the outgoing light, but if it's constant, it's just like a constant function. So there's no variance to it. So actually what we can say, the BRDF in this integral, we can just explain it with the single scalar done. We don't need to integrate over it anymore. Does it make sense? Okay, so since it's a single scalar, we can just pull it out of the integral. So the BRDF now, if you assume that all surfaces in the scene are diffuse and none of them have any shininess to them, you can just take the rendering equation, you pull out the BRDF. Done, easy. Now, the second simplification you can make is that you say, well, maybe there is a constant number of light sources in the scene, and each of the light sources is approximately a point light source, which basically means the point light source is really small, and there's a constant number of these light sources within the scene. So maybe there's like 10 of them in the scene, right? And then that basically says that that you don't have to integrate over the angles anymore, because and there's a constant, like there's a fixed number of them, so you just sum up for all of the different light sources. So if you're interested in the amount of light that is reflected, like if this surface was perfectly diffuse, which means it doesn't have any preference for the direction where light is coming from, then the outgoing light at this thing is just going to sum up over all of the light sources, how much light are they like emitting in this direction. So it's just a sum over some fixed number of light sources. Does it make sense? Good. Okay. Diffuse light. So then how do you account for the color of a given surface? this is basically going to be that the color of the surface that you're observing is a combination of the color of the light that is incoming and of the color of the surface itself. So if you, this is pretty intuitive. If you have a surface that is red and you have a white light source, then you all know this, the surface is going to appear as red. But if you have a surface that is, for instance, like, I don't know, purple, but your light source is blue, then maybe the surface will appear under a different color. And so that means that, like, maybe you are admitting that, okay, you have a different number of light sources in the scene, and each of the light sources could have a different color. And then you can just say, well, there's the color of the surface, and then there's the color of the light source. Okay, all univectors, light locations matter. And this is the thing, if you have diffuse surfaces, right, then the locations of the light sources matter, but the locations of the eyes does not. Okay, whatever. And then there's one more thing to keep in mind. Like this right now would be kind of a stupid model, because imagine that you want to get the color of this point, but there's a light source under the table. So like, then how do you account for the fact that the light source under the table doesn't contribute to the light that is being emitted from this point? And computationally, this is modeled very simply. You say you take the surface of the surface, the surface normal, and you say, okay, if the direction, like the direction vector of that surface point towards that light source, if it has a dot product that is smaller than 0, so it's like it's not on the same side of the surface, then you just say that the contribution of the surface of that light source to the outgoing light is exactly 0. Does that make sense? Okay, so now we have modeled the scene as Lambertian. So no surface can be shiny right now, so there's no shininess allowed. And honestly, like, that, if you try to render that, it looks like very boring. It doesn't look good at all. So like, shininess is quite important. Like, so we're going to account for two things. One is exactly shininess, which is called like specular highlights or specularity. Specularity basically means shininess. And the second part is going to be ambient light. And ambient light is actually a huge hack. So the trick is kind of, imagine that you have a room that is red, and now you put a white table into the room. And the light sources in the room are also all white. Then right now, as we had modeled it so far, the table would appear, like if you picked a point on the table, the color of the table would be white, right? Because you pick a point on the table, and then you like just sum up over all of the light contributions of all of the light sources, and the table will be white. But you all know that if you put a white table in a red room, the table is going to appear red, because there's light that actually bounces around in the scene. It picks up the red color from the room, and then it bounces back to the table, and that's then the light that you actually observe, right? So like, just empirically you observe, if you put a white table in a red room, it's going to look red. And like in this like very simple Phong shading, or like in this very simple shading model, we're going to account for that with a huge hack, which is just, we're going to say there's an ambient term. And the ambient term is basically saying, for any point we're looking at in this room, we're just going to say there's a constant component. It's kind of like saying there's a light source that is always, that is hitting every point in the scene, and that light source is just going to have a color. So you're basically saying, in this red room, we're going to not actually model the fact that light bounces first against the wall and then into the table. Instead, we're just going to say we have like a ambient light term, which is just a red light source somewhere in the room. And it turns out that is kind of, so we're talking about computer graphics, right? These people were very practical. They wanted to build video games. And for the video game, they just needed something that looked fine. So this kind of looks fine, so good enough. So we're just now going to add an ambient term. So like, now the surface has a color, and this ambient light thing has a color, and then it's the dot product. So it's kind of, well, makes sense. And then you have the second term, which we just discussed, which is like, you have again the dot product of the color of the surface with the color of the light. That also makes sense. So for instance, if you have a red light but a green surface, then it's exactly it's 0. But if you have a red light and red surface, then it's going to be meaningful. And then the last part is the specular reflection. So specular reflection is basically modeling the shininess. And how are we going to model the shininess? Shininess, as we had learned before, is exactly this part about like the BRDF being direction dependent, right? But we don't actually want to do any kind of integration or something like that right now. It's way too complicated, and it's like we just want to look kind of reasonable. And so we're going to make another little hack, which is we're going to take the dot product of the surface of what is E? Sorry, forgot the notation. What is E? Right. So we're going to take E as the outgoing light direction. So like you're looking, it's sometimes called the I vector in computer graphics, exactly that's why it's E. So you have this outgoing direction, and if the surface would be perfectly specular, then all of the light would be reflected at the same angle where it entered the scene, right? For the perfect mirror, as we had discussed before, like the light is going to enter the surface and it's going to exit. It's going to be Dirac exactly only for this one vector that is at the same angle relative to the surface normal. And now we basically want to do something hacky. We basically want to say, okay, we want to model the surface as shiny, which means that the closer we get to that vector, the closer that our I vector gets to the vector of the perfect reflection, the more we want to see the color of that light source. Does that make sense? So the closer that vector gets, the more we want to see it. And this is like, this is kind of funny. This is perfectly hacky, zero physical interpretation. We're just going to take the dot product of these two vectors, and then we're going to take it to some power. And then if the higher the power, the faster it'll fall off. So then like the more specular, right? And then again, the maximum is just saying if the dot product is smaller than 0, like it means then we don't want to account for it. So this is basically the idea of Phong shading. And you can see how you could code this up. You could like literally code this up. People code this up in an undergraduate graphics class like me a long time ago. Lambertian, so we have like a Lambertian surface term and we have a specular highlight term. It's still assuming that we have only direct lights though, so it's like still just a number of constant lights. Okay, and this is then what it looks like. So you have the ambient term, which is basically just, I don't know, maybe this is a white like object, but the ambient light is kind of blue. Then you have a diffuse part, which is like the surface is maybe blue and it's like reflecting the light source is kind of like somewhere over here, and this part is black because exactly this dot product of the surface normal and the light source. So this part is darker than the other side that is facing the light source. And then the specular reflections is basically saying, okay, you now have a few specular highlights. And then when you render it and you just take the sum of all of these, then it's going to look like that. And then it's like kind of, okay, fine. And maybe if you remember playing like video games from the 90s, they all kind of look like that. I guess maybe from the early 2000s. Questions? Please, only questions that I can actually answer. Yeah, so this is now assuming that you remember what meshes are. Do you remember what meshes are? So meshes were this way of parametrizing surfaces as like you have vertices, right? And then you have faces that connect the vertices. And now we can basically say, imagine I now give you a mesh and I give you a number of light sources. So I basically tell you there's one light source here, there's one light source here, and you have like a sphere that is floating here. And the sphere is parametrized as a mesh. So there's like a number of vertices and they're connected to make like faces. Now you can basically take this equation and for every surface, when you pick a view angle, right? You say like I'm looking at the sphere from this angle, and now for every pixel you can basically trace a ray through that pixel, and you can ask it, okay, my ray hits the sphere at this point. What's the color of this point? And now you can stick it into the equation we just discussed, and that tells you what the color of that point is. Does that make sense? Okay, now there's a funny thing. So like let's say we do exactly what we just discussed. And what we're going to say is, well, it makes sense. We have parameterized this mesh as we have parameterized the sphere as a mesh, and we discussed previously that meshes are basically piecewise linear approximations of the surface. So it's like lots of little facets, right? So what's the surface normal of the sphere? We can say the surface normal of the sphere, for instance, is exactly, well, the surface normal of each of the mesh phases. So each mesh phase has its own little surface normal because it's a piecewise linear approximation of the surface. So we can use that as the input to our little equation that we just derived, and then the sphere is going to look like that. Right? That makes sense? Okay. So it turns out you can do a little bit better. So one thing you can do is you can say, actually, we're going to have the surface normal be stored at the vertex. It's not going to be stored at the, it's not actually going to be stored at the, oh my God. This is the downside of having too many steps in your slides. It always takes forever to go forwards and backwards. Okay. Actually, I skipped a step here. So you basically compute the, you could do slightly better by saying we're going to have the surface normal, we're going to evaluate the surface normal for this triangle at the 3 vertex corners. We're going to calculate the color at each of the 3 vertex corners, and then we're going to interpolate the color onto the face. So we're interpolating the color. And that looks like something like, this looks something like this. So interpolating the color gives you something that already looks a little bit more like a sphere. And now the final thing you can do is instead of interpolating the color, which basically gives you a linear interpolation of the color at the 3 vertex corners, you can actually say we're going to interpolate the normals at each of the vertices. So at each vertex, you're going to have a surface normal. And now when you let's say you shoot a ray, right? And now you're asking what's the point at this coordinate. What you're going to do is you're going to interpolate these 3 normals, and then you're going to stick that normal into your rendering equation, and you're going to evaluate the equation that we just derived using that surface normal. And then it actually looks like almost like an actual sphere. So even though the surface is parametrized piecewise linear, just by doing a little trick by interpolating the normals that are stored at the vertices, you can kind of get to something that is looks reasonable. Okay, so this is the very bottom of the photorealism list, as you might imagine. So Phong shading is like the very bottom of photorealism, even in the sense that it's actually not physically based. And there's lots of things that consequently it can't do. It can't really do shadows that are cast from one object onto yes.
Are the vertex normals, like, are they just the average base normals vertex? Or like, how do you compute the vertex?
It's like literally, you don't compute it, you literally store it. You basically say like each vertex will also store its, will have a, yeah. It's like stored in the mesh. Other questions? Yes?
The normals at each of the vertices, are they the same, like for like a given mesh?
Yeah, you would be storing a different normal for each vertex. But I think I think that's not what you're asking. What you're asking is, like, do the pairs of faces and vertices have different normals?
Yes, because like a mesh is like a face and like 3 vertices, right? And usually you have like one normal associated.
Yeah, you would have one normal associated with each vertex. Now.
In the second case, then you would store like the normal for each vertex.
Yeah.
So it's a completely different representation.
Yeah, you would literally, but I mean, at the end of the day, it's just a list, right, in the computer, and so you would just basically say, where do I store the normals? Do I store the one normal per face, or do I want to store one normal per vertex? But it's exactly a different representation. Okay, and so there's lots of things that Phong shading can't do. It can't do shadows, and like, just notice, you might say like, oh, but like, oh my God. You might say, well, but this was a shadow. No, but this is so where did this gradient come from? This gradient came from the light source being there, and this gradient came from the dot product of the surface normal with the direction of with where the light source was. So this is where this color gradient came from. This Phong shading model cannot actually parameterize shadows. What I mean by that is, okay, the light source is somewhere over there clearly. Now imagine there was another object in between. You can look at the equation. There's no way for you right now to account for the fact that something might be blocking the light source. Right now, you're just literally iterating through all the light sources, and you're just like summing up all of the different contributions. Okay, so Phong shading can't deal with shadows. It can't deal with refraction. Like basically, Phong shading doesn't deal with anything. It's easier to make a list of things that Phong shading does deal with than a list of things that Phong shading doesn't deal with. It basically doesn't deal with anything but the things we discussed. Unsurprising. Okay, so now we're going to ray tracing, which is basically one step more involved. And I think the intuition of ray tracing, I think, is actually easier than the intuition of Phong shading. So the intuition of ray tracing is basically to say, we have our image, and we have our eye, and now we have a pixel. And the pixel we're going to model for a moment just as a single light ray. So we're going to say, for this pixel, if we want to figure out what the color of this pixel is, we're going to shoot a ray through that pixel. And maybe you remember how to parameterize rays as a function of the pixel coordinate from lecture number 2. So this is what you would be doing. Who remembers that? Yeah, good. Careful, I might ask you if you can. So what's the equation? This is the equation, right? So like it's this whole thing with like the intrinsics, and the whole thing with like camera conventions and whatnot applies. Okay, but basically we're going to, for each pixel, create an array from the eye that goes to that pixel coordinate. And then we assume that we have a list of objects in the scene. Each object is a mesh. So this is the way computer graphics does it, right? We have a list of objects in the scene. For each of the objects, we're going to test if our array intersects with that object. So for instance, here we have 5 spheres. We're going to test for each of the spheres if the array intersects the sphere. And then there's another thing, which is like you want to really only consider the first intersection, because any intersection that happens afterwards, it doesn't matter anymore, right? If the surface weren't transparent. And then you just want to say, okay, record this intersection. And then finally, once you have found all the intersections, you're going to take the pixel and you're going to say, we're going to account the color, we're going to assign this pixel the color according to the equation that we just derived, or like according to like some equation that tells us the color of this pixel as a function of the surface normal and the light sources. So this is the idea of ray tracing. And now the trick is that like we can now add different levels of complexity to account for different lighting effects. So let's say, for instance, okay, but this makes sense. Okay, we're going to skip this. How do you find the intersection of a ray with a sphere? I think this is fine. Let's say, for instance, we want to deal with reflections. So let's say, for instance, we want to say, well, the sphere is like is specular, and now we want to account for the fact that this point here gets a color that is dependent on the reflection of this point here at this surface point of the sphere. And like one level of complexity we can go to is we can just like add a term to our shading equation that just accounts for that thing. So right, we had these terms before. You might have an ambient term. You might have a diffuse term, which is this term here. You might have a specular term, which is basically just note that the specular is the shininess, but it's only the shininess that is caused by the lights, right? You're just iterating through the light sources, and there's like a little shininess that comes from this surface reflecting that light source. But now there might also be a term of this surface actually reflecting the light that comes from this surface here. And now the question is, how would you go about computing? I mean, now I gave it away, but how would you actually go about computing? How would you actually go about computing that term? Like now you want to implement this in a computer, and you somehow want to say, okay, like this surface point, where does it get its color from? It gets its color from the ambient light, fine. It gets it's diffuse, so it gets its color from all of the light sources that are visible, and that's the diffuse term. Now it gets a specular component, which is the shininess. So like that's the specular component. And now it gets a component of it also reflects the light that comes from a different point in the 3D scene. How could we go about computing that? Well, we could do it first order, and we could just say, how about we just move the camera to that point, and we're going to look in that direction, right? You could basically say, well, we're going to place our camera here, and if we only want to deal with first order reflections, we're going to place our camera here. We look in all of the possible directions, and we're always going to just run our Phong shading algorithm one more time, which then tells us what the scene looks like from that perspective, which is exactly the amount of light that you see in every angle, and then that is the thing that we're accounting for in the reflection, right? And now you actually start to see like where many of the problems come from. The problem is that this is, if you do this, if you want to do a good job with this, it becomes recursive because you might want to consider all of the directions, but there's like lots of little hacks you can do. So for instance, you say, well, okay, technically we would have to place the camera there and look in every direction, but maybe there's only one direction that really matters because it's a reflective surface, like a mirror, for instance, and if it's a mirror, then there's, for instance, only one direction where we actually care about where the other light is coming from. And so that's, for instance, one little simplification we can do. So we can say, well, we're going to just generate a single direction. Like we're going to just say we're going to place the camera there, but we don't actually look at many directions where the reflection could be coming from. We're just going to generate the most likely direction. And the most likely direction, of course, if you had the surface normal, for instance, might be exactly the outgoing, like you have the incoming eye ray, and it might just be exactly mirrored the incoming eye ray. And then you're just going to calculate that thing. But if you want to do a good job with this, it becomes recursive, right? You like because now you have to compute the color of that ray, but maybe that ray also has a component that is caused by lots of reflections throughout the scene. So now you would have to do the same thing again. You would have to place your camera, and so it becomes recursive and it blows up. So in practice, you would just like curb it. You would just say, okay, we're going to do single bounce, basically. We stop after one bounce. Or not. And there's, so you can just either hard code it, you can say this is the maximum depth, so you can say we're going to stop after one bounce. Other reasonable things might be the surfaces might vary in shininess. So clearly, if you look at a mirror, then it's really important that you account for the first reflection. But maybe if you hit a piece of paper, the piece of paper does reflect stuff a little bit, but not that much. So maybe you can just ignore it. So you say, oh, maybe I do my recursion until I hit a surface that doesn't reflect much, and then I just stop it. Or you say we're going to stop it after one, or Okay, refraction. We're going to skip. Well, actually, no. No, we're going to skip it. Whatever. Okay, no, we're going to talk about it. So who knows what refraction is? I'm going to otherwise talk about it. So it's like, okay, refraction is the fact that light is bent by like glass, for instance, right? So you can account for that by tracing this ray first to the surface of the glass, and then you trace it then the light ray is bent, and then you have to trace it outside of the glass again. So pretty straightforward. Okay, and now we come to practical considerations. And actually, interestingly, last year I was like not very excited in talking about this part because these things in inverse graphics weren't all that relevant until recently, and I didn't think they would become too relevant, but I was very wrong, as we're going to see shortly. Obviously, runtime is a problem with all of this. Like, as you can see with the recursive nature, for instance, like, obviously you can't recurse to arbitrary depths, and this is a rather expensive process altogether. Okay, so there's lots of ways in which you might be able to accelerate this process. So one way of accelerating this process is by bounding boxes. So let's say I give you a mesh, like you build your scene out of lots of meshes. You have like a list of meshes, right? And now you can do a very straightforward acceleration, which is I give you the mesh and you draw a bounding box around the mesh. You say this mesh is contained in this bounding box. So the mesh might consist of 1 million vertices. So normally, if you were to shoot your ray, you would have to test for each of these 1 million vertices if the ray is intersecting that faces, if that ray is intersecting the surface or not. But now, of course, if you have a bounding box and you know all of the vertices are contained in this box, you just have to check, like the first thing you might want to check is if the ray intersects the bounding box or not. And if it doesn't intersect the bounding box, then maybe you don't have to test whether all of the vertices inside, whether all the faces inside the bounding box intersect the ray or not. So very simple concept. And then, of course, it becomes a question of level of detail, so to speak. Like, it's a trade-off. Like, at which level do you draw the bounding boxes? You can draw a bounding box around the head of the bunny, or you can draw a bounding box around the rest of the bunny. But you actually already know of a way of dealing with this. You can, of course, build a hierarchy. So let's say we have like a link of these little, what are these things called? Clips? Paper clips, thank you. Paper clips. You could draw one bounding box around the whole chain of paper clips. You could draw one bounding box about each half of the paper clip. You could draw one bounding box around all of the paper clips. And ideally, maybe you build a hierarchy of these bounding boxes. And then when you shoot a ray, you just test it against each level of the hierarchy. And this, for instance, makes sense, right? If each of these paper clips has 1 million vertices, then this really pays off. Because just one level of the hierarchy, you would still have to test against 4 million vertices. Yes?
Similar to what you talked about with the different resolutions of the box array?
Yes. Very good question. So you actually already know a way of building such a hierarchy, which is via an octree. Right? So, okay, so this is exactly the next slide. Thank you, Cairo. Create bounding hierarchy. So how do you build this in practice? You could build it with exactly an octree. So you have your scene, you have lots of objects in the scene, and you could build exactly like an octree that says, I'm going to say in each voxel of the octree, I'm going to recurse and build like a higher and higher resolution octree until in each voxel there's like 50 vertices contained. And then this is just an algorithmic way of building such a hierarchy. Does that make sense? Cool. And here's a figure from a paper from 2021. And I'm just throwing this up to show you that this is still a relevant thing today. So this is a paper from NVIDIA from 2021. It's called Neural Geometric Level of Detail. And this figure tells you exactly what's going on. So like, let's say you have like some kind of geometry. They say we're going to build an octree. Well, actually, I'm not going to go through detail in the figure. But the thing that I want to get to is finally they have a visualization of the rendering algorithm. And as you can see in the rendering algorithm, they implement exactly this thing. They basically say, look, in our octree, we keep track which voxels contain something and which voxels don't contain something. And when we shoot array, then we really only have to consider the voxels that contain something. And then the thing on the right, we don't understand yet. We're going to talk about that next lecture. OK, does that make sense so far? Good. So then next, we're going to talk about shadows. Again, there's like a hacky way of dealing with shadows, or like a funny way of dealing with shadows. So let's say you have a light source. Like first, some terminology. Let's say you have a point light source, like a light source that is really only emitting light in all directions equally, but it has no spatial extent. It's a point. Then, if you have an object in the scene and the surface down here, you get a shadow that is like perfectly sharp. Like the boundaries of the shadow will be perfectly sharp. But now, let's say you all know this. If you have a light source that has spatial extent, like the sun, which is like has significant spatial extent in the sky, then what happens is that the different, so to speak, the two different, how to call this, like the two different sides of the sun, they like, well, the two different sides of the sun in an extreme sense, they basically generate two different shadows, right? And infinitesimally, of course, every point on the disk of the sun generates like its own shadow, so to speak. And so you will have one part of the shadow which is really dark because like absolutely no light from that light source reaches it. And then you have parts of the shadow which are brighter because there are some parts of the light source that still trace rays to that part of the surface. And this is called the umbra, like the part that is perfectly dark, and then the penumbra is this part on the right side. And like, what does that look like in practice? If you have a light source like this and you have a surface like this, then you'll get shadows here. There's more terminology. Okay. How do we add shadows in ray tracing? I think you might already have an idea of how to do that. Okay, so now we have this case that notice so far, right, like Phong shading, as we had discussed before, the shading algorithm that we discussed before didn't have any notion of being like of occluding light sources and of shadows that are caused by objects that are between the light source and the object. We just iterated through all the light sources and we just added the contributions of all the light sources. And so now, maybe not too surprising, you can just add a way of like testing whether a light source is visible or not, right? So now you can just say, well, we're only going to sum over the visible light sources. Surprising. And you might ask, how do we figure out if a light source is visible or not? An easy way, and this is actually how it was done in video games until, I think it's probably still done in many video games today, is you take your camera and you virtually place your camera at that point and you just look at all the light sources. And you ask, like when I render, when I place my camera here, and I look in the direction of that light source, is there any, like, and I put it into my rendering algorithm, is there any surface I'm intersecting or not? If I'm not intersecting any surfaces on the way to the light source, then I see the light source, and if I intersect a surface on the way, then I don't see the light source. So this is kind of a funny little trick. And now, with all of these things together, we can actually already get some pretty funny effects. So like all of these effects together, allow you to, so this is, I think, from a paper from the 80s. So all of this stuff was developed in the late 70s and early 80s. And this is a figure from a paper. So this probably took like, I don't know, 6 hours to render on like whatever machine they had back in the day. But with all of these tricks and like methods that we discussed so far, you can already get images that look like this. And this is something you could, if you wanted, code up yourself in C++. You could, it's not, I mean, it's a pain, but it's not that complicated. It's basically just taking arrays and testing whether, like instantiating triangles and testing whether array intersects with the triangle and then sticking it into this equation. Okay, so we now have one more level on our hierarchy of photorealism. So, I mean, still not exactly what I would call photorealistic, but we're getting there. Okay, so the next thing, how can we actually deal with soft shadows? And this is now basically just I think on a high level, the story that we can tell is that so far we have approximated many effects that are actually statistical effects with like things like, oh, we only take a single sample from that thing. So let me give you an example. When you dealt with the reflection, we were already saying that if you look at a mirror, it is in fact true that if you shoot a ray, like the only other thing that you have to look at is the exit ray that is just mirrored along the surface normal. But if the surface is even slightly rough, then in order to get a good idea for that, you actually would have to consider lots of rays that are kind of like varying slightly in the direction. You would have to integrate among all of these rays. So basically, the story of going from a very simple model to photorealism is a story of going from approximating this integral at like more and more detail, which basically comes down to sampling more and more light rays. So for instance, when we're computing our shadow, we were just discussing the umbra and the penumbra, right? So we were just discussing this case where, well, actually this light source, if it's a point light source, it's totally fine to like just check whether the light source is visible or not, because the light source doesn't have any spatial extent. So if you move your camera here and you render the scene from this perspective, looking at the light source, you can just check if there's anything in the way, and if there's nothing in the way, you see the light source, great. And if there is something in the way, you just set the contribution of that light source to 0. But now, if the light source has spatial extent, you can't do that anymore, because now there's like lots of different rays coming from the light source, and they exactly lead to this differentiation in shadow. So what do? Well, you basically shoot, like you don't just generate one ray that looks at the light source, you generate lots of rays that look at the light source. And now what the contribution of that light source is actually going to be is basically the ratio of all of these rays that are being occluded by the object in between versus the rays that are not being occluded. So you're basically now going to take a statistical approximation, which is going to be the mean. So you shoot lots of rays in the direction of the light source, and you're going to take the mean, and for each of the rays you test whether some part of the light source is visible or not, and then you're just going to take the mean of all of these contributions, and that now tells you the light intensity at that point. Does that make intuitive sense? Questions? Great. So now we can basically, this is actually something that is quite a significant improvement in photorealism, right? So here we have exactly the case that we have a surface, and this surface gets a contribution from that light source. It's the only light source maybe in the scene. And imagine for a moment this was a point light source, so then it would just be approximated by a single point. And then this shadow would look like what? It would just be a perfectly crisp sphere, right? But now the light source is actually a surface light source. It's maybe a window, for instance. And now we basically can say for this point down here, or like for this point down here, now we have to consider more than just a single ray. We have to consider all of the rays that go onto the surface of the light source. And how can we approximate that? Well, we can approximate it with a varying number of rays. So for this light source, we can say we're going to pick 4. We're going to trace 4 rays to the 4 boundaries of the light source, and then you get something that looks like that. Or you can discretize it more finely, so you discretize the light source more finely, and for each of the points now you have to trace 9 rays, and you get something that looks like this. If you discretize it even more finely, then you would get an even like a softer shadow, and so on and so forth. And soft shadows used to be like, I still remember like when you read like video gaming magazines in like the 2010s and stuff, and the early 2000s, then like soft shadows were something that people would start commenting on. They'd be like, oh, this game has soft shadows. It looks so much better than these hard shadows from like the old video games. Okay. And okay, of course, I mean, same story again. Like if you have reflections, the same is true, right? Like previously we generated only one ray. Like if we accounted for this, if we accounted for the reflection of this object in this object, you can say we're only going to generate a single ray, and then you can approximate perfect reflections, or you can say we're going to not do that and we're going to shoot more rays, and then we can deal with the fact that it's actually like a soft thing. Does that make sense? Cool. So long story short, like more and more rays. The better you want to approximate this thing, the more rays you trace. And this now, okay, so but the thing that I the thing that I want to point out is that all of this is driven by the objects in the scene. Like all of this basically assumes that you have a list of objects and you have a list of light sources in the scene. And if you look at how we approximate this integral, it always ends up being like for loops over either the objects or over the light sources. And we can like discretize the light sources a little bit, and then we shoot more rays, or we can generate more rays. But like basically, it's always loops over the number of objects or the number of light sources in the scene. But this gets us reasonably far. So this is called like distribution ray tracing, and the idea is just, well, you have these like these effects that are modeled by that you have to approximate as an integral. And now beyond ray tracing. So this is now where basically we enter the domain of path tracing. And there's like some effects that ray tracing can't model. So you have, for instance, diffuse interreflections. Like there's like two diffuse surfaces, and they're like the light really bounces around in the room, and the light bounces around and picks up different colors from diffuse surfaces. And this is then, if you want to get to perfect photorealism, and this is now the thing that happens when you watch a Pixar movie, or if you watch a movie that is trying to be photorealistic, what's the algorithm they use? This algorithm is called path tracing. And actually, intuitively, I think you already get an idea of what path tracing might be. Path tracing now really ends up being basically trying to approximate this rendering equation by just Monte Carlo approximation of this rendering equation. So what does that mean? In many ways, it is actually getting simpler. For each pixel in the scene, you create a ray from the eye through that pixel, and then you're just going to generate, without caring basically for the number of objects in the scene or for the number of light sources in the scene, you're just going to say we're going to just discretize the space of all possible directions, and we're just going to shoot rays in like random directions. And the more rays, and then we're going to pop those on the stack, and we just call this project, we call this process recursively. So like instead of, right, previously we basically said, oh, we like shoot a ray here, and now here we basically ask, okay, where are the light sources in the scene, and where are the other objects in the scene, and we basically try to reason about like where's the light coming from. Now in path tracing, there's still a notion of this, but mostly it's really just the concept of really the contributions of the 3D scene to the color of the surface are very, very complex, and there's like a contribution from basically every direction. It's just varying degrees of contribution from every direction. But if we want to actually photorealistically render it, we have to basically consider every possible direction that is coming into this point. And so the idea of path tracing is basically saying, well, you shoot the ray, and then you generate secondary rays. Then you trace each of the secondary rays to like the next intersection. You generate the third, how do you say it, tertiary rays. And now I forgot what comes after tertiary. And when do you stop? You stop when the ray ends up at a light source, because you know that all of the light that is within the scene has to be emitted from somewhere. So you're basically going to stop once your light ray hits a surface that is, for instance, an emitter. And then you basically trace back the contribution of that light source through this whole path, and then you sum up through all of the different possible paths. Does that make sense? Come on. Okay, good. So, and now we're basically down to the actual. Now we basically we can actually use this continuous BRDF that we talked about before, because now we are really literally we shoot a ray to the surface, and now we're integrating. We're just taking the sum of all possible directions weighted by the BRDF. So now we can have a continuous parametrization of the BRDF, like a function. We might call this function. And then we just integrate over all possible light directions. And this is now actually, I mean, surprisingly, the stuff that gets you to photorealism. So what I guess is the interesting takeaway, like this image, which I guess it's not perfectly photorealistic by today's standards anymore, but it looks like pretty damn good. And these kinds of images that you see here, there's like, it's just crunching the numbers for this rendering integral that we just discussed. So all of the complexity lies in modeling the geometry with like meshes, and then modeling the materials via these BRDFs, like which are basically the ways in which you know that the surface is reflecting light. And then you have some effects like the glass and so on, which have like these refractive effects, which you have to deal with in a slightly different way. But fundamentally, it's just crunching the numbers using the rendering equation. And that gives you basically, gets you really, really close to photorealism. Well, we're going to skip that, whatever. So there's like a bunch of different ways of accelerating this. And now because this is basically an approximation of an integral via basically taking a bunch of samples, if you take more samples, you get a better approximation of the integral. So what we're going to look at now is we're going to look at approximating this integral by admitting more and more samples of light rays. So we might generate more and more light rays at of course there's maybe only one light ray that you shoot for every pixel, but now at this point, how many of the secondary light rays do you actually trace? And then how many tertiary light rays do you actually trace? And so you can basically say we're increasing the number of light rays that we're using to approximate this integral. And as you can see, as we are increasing the number of light rays, so this is, actually forgot what SPP is, but this is many light rays and fewer light rays. And the only other thing that is worth noting in this thing is that in a previous lecture, I had a thing, what changed since deep learning? You could ask again, what changed in this kind of photorealistic graphics in deep learning? And the answer is basically nothing, except for one really, really funny or interesting thing. So when Pixar makes a movie, how long do you think does it take to I forgot the exact number, but the Monsters Inc. Do you remember that? Who remembers Monsters Inc.? Okay, a bunch of people. I don't exactly remember the number. Maybe someone could Google it. If you Google rendering one frame of Monsters Inc. And how long it took to render one frame of Monsters Inc., if I remember correctly, it was around 20 hours. So rendering one frame of that video took 20 hours because we took a pixel and then we ran this algorithm, which is ultra expensive because we're tracing literally billions of rays for any given image, right? One image has a resolution of I don't know what the resolutions were back then. Let's say it's 1,000 by 1,000, so that's 1,000,000 pixels. So just the primary ray that you shoot through every pixel is 1,000,000 rays. And then for each of these primary rays, you're going to generate 10, it's not 10, it's more 100 or 1,000 maybe, 1,000 secondary rays. And for each of these secondary rays, you're going to generate another. It's crazy. It gets ultra expensive. So did someone Google it? How long it took? Yes? 29 hours. So a single frame of Monsters Inc. took 29 hours to render. This is insane. So one thing that deep learning did, which is really funny, is deep learning basically said, okay, this is basically like a noisy image, right? So this image has fewer rays than the other images. So one way to improve this image is to increase the number of rays. Or here's another thing you can do is you can train a neural network to take a noisy image and map it to a less noisy image. So you can train a deep denoiser, and you can train it supervised, right? It's very easy. How do you generate the training set? You take a frame of Monsters Inc., you render it with some low number of rays, and then you keep rendering it, and you get one with more rays, and now we train a neural network to map from the noisy estimate to the less noisy estimate. And that is actually something that Pixar does in production. So they actually have a neural network that does denoising. And one thing to think about is that this is especially useful when you are the person who makes the movie, who actually animates the movie. What is really important is that while you're animating it, you would like to be able to look at the thing that you're animating, right? So you change something, and now you would look at the result of what you just changed. Unfortunately, that takes 29 hours. So if you change something, it takes 29 hours to render. So that's not great. So in fact, what people do is they look at these slightly noisy images, right? So in fact, if you've ever worked with Blender, you've actually seen this yourself. Blender actually, usually all of these 3D editing suites, they implement different levels of this photorealism tree. They have different options to render the same 3D scene. And oftentimes when you build the basics of the 3D scene, you just pick a really basic renderer, which might be one of these path tracers we just discussed, which doesn't have soft shadows, it doesn't have reflections. It basically renders it really cheaply. That just allows you to edit it in real time and immediately see what happens. And then as you get closer to completing the photorealistic scene, you switch to path tracing, and then you maybe keep in the real-time preview, you keep the number of samples low. So what you would be looking at would be an image like this. So you would basically see a noisy image of the scene, but it allows you to edit it and immediately get feedback. And then when you finally render the thing for like production, then you press a button and it takes 4 hours for the frame to render, but then it looks really good. And this is what this denoised mean here. So like this basically was saying, like, look, you can take few arrays and you can just denoise the image. And if the image didn't look that noisy to begin with, you basically get something that looks perfect. Okay, whatever. Okay, summary, different levels of photorealism. And the ground truth is basically the rendering equation. And now, does anyone know what are effects that aren't captured by the rendering equation? Yes? Caustics? I think caustics you can actually, because I think caustics are just effects of refractions. But it's a good point. Does everyone know what a caustic is? It's like if you look at the bottom of a swimming pool. And I think caustics are because it's just like the water bending the rays in there. But good guess. So can someone think of another effect that maybe we haven't accounted for so far? One effect is diffractive effects. So for instance, if you look at the wings of a butterfly, they have this like really weird property, right? Like that they have sometimes this, I don't even know how to describe it. Like they have these like, they have this like super blue sheen to them, or like they have this weird sheen to them. And these are actually effects that are caused by the surface of the butterfly wing having some kind of geometry that is very regular. So it's a very symmetric and very regular structure. But it is on the size, it's on the size of the wavelength of the light. And then what happens is that as the light hits the surface, you have the wave effects of light that now start to matter. So there's diffraction. So the light acts as a wave, and the butterfly wing basically diffracts the light such that there's productive and destructive interference, and then you get these like really weird effects of the butterfly wing. And this is, for instance, something that isn't done in path tracing. But you can, as you might imagine by now, you can, of course, augment the path tracing thing with a way of taking care of diffraction. For instance, you can say, oh, I'm tracing rays, but for each ray, I keep track of like the length of the length of the total path that I traced, and then you can also model diffraction and interference effects. So you can basically stuff this with more and more effects. And another thing that is funny, actually, maybe I'm going to put it at the lecture of the next slide. You can actually now take this rendering integral and you can build a camera in Blender. So you can take Blender or any kind of renderer that is actually, it's really a simulation. You're really simulating how the light bounces around in the scene. What that means is, for instance, you can build a box in Blender and punch a tiny hole into it. And then you place it in the scene and you press render, and it is going to, and then in the end you can go into the box and you can look at the back side of the box, and what are you going to see? You're going to see the image of a pinhole camera at the other side of the box. Because Blender is literally simulating the light transport through the scene, and you can build like lenses and you can assemble them into cameras, and then you can press render. And if you have a lot of time and you can like render billions and billions of rays, then eventually, like, because you're actually approximating the ground truth physical light transport, you can like build a physical camera in Blender. And there's a guy who did this, and it took like, I don't know, 600 hours. He has a video of like a YouTube video where he like goes through all of these. I'm going to show it at the beginning of the next lecture. It's really funny. Okay, in the last 2 minutes, I just want to point out a few effects that we didn't talk about. One effect that we didn't talk about is depth of field. Who knows what depth of field is? Okay, so depth of field happens because your lens is actually not a pinhole camera. So far we always talked about cameras, and we always talked as if the camera is like a box that has a hole. And we basically hand waved. We said, oh, if you put a lens in a camera, it's kind of the same thing. And it's true, it's kind of the same thing, except for a few effects. One of these effects is as the aperture, which is the size of the hole, grows, and you put a lens into it, then what happens is that actually there's an effect where there's only one plane of the one depth at which there's a one-to-one mapping of pixels to 3D points on that depth. But for all other points, each pixel is actually getting a contribution from lots of different 3D points, and that's what depth of field ends up being. So for this camera is like focused on this depth, and for that depth, it's a one-to-one mapping of surface points to pixels. but for every other depth, you're averaging over like a large area, and that's why it ends up being blurry. So this is, for instance, an effect that we didn't discuss about, but that does actually matter if you do inverse graphics later. Another important effect is dynamic range. That's because your camera is a digital sensor, which means every pixel is, in the end, producing a number. But it turns out that light in the real world and like